Ooh, ooh. Boy, those photons really pack a punch. Today we need to learn about the energy of light, don't we? You know that violet light is violent. Maybe you even know that gamma rays have the most energy of any type of electromagnetic radiation. You know that light energy is used for making plants grow. And maybe you even know that some of the energy that goes into a light bulb is turned into heat instead of light. Energy and frequency relationships. We've looked at this image. We know that this top wavelength has a very, very long wavelength and a low frequency, and you know that the one on the bottom has a very high frequency and a very low wavelength. But now let's talk about energy. In class we've said that violet light is violent, and so that reminds us that these violet waves with very short wavelengths have a high energy. So we can say that energy is proportional to frequency, and we can also say that energy is inversely proportional to wavelength. Today we're going to take a look at a new equation. E equals h times nu, where E is the energy of a photon expressed in joules, that is the unit, and where h is something called Planck's constant, which is always 6.63 times 10 to the negative 34th joules per hertz. So you just plug that in every time, it's the same number. And then this symbol right here, which is nu, that's frequency, and you know all about nu. I have 4 different sample problems. The first one is maybe the simplest. What is the energy of a photon that has a frequency of 3 times 10 to the 19th hertz? We know these two equations, C equals lambda times nu and E equals h times nu. Now our question says, what is the energy? So we need to use this equation on the right. And so let's just plug in our numbers. H is always 6.63 times 10 to the negative 34th joules per hertz. And we're going to multiply that times the frequency, which is given in the problem, 3.0 times 10 to the 19th hertz. So we multiply those two numbers together, and our answer is 1.99 times 10 to the negative 14th. We also need to think about the energy. So we've already said that energy is defined in terms of joules, and if we look at the units here, we had joules per hertz multiplied by hertz. So hertz was on the bottom here, hertz is on the top, so that means that those two cancel each other out, and the only thing that survives is joules. The second problem asks us to determine the frequency of a photon that has an energy of 2.5 times 10 to the negative 31st joules. So we have to get the frequency. Well, we have two equations, C equals lambda times nu and E equals h times nu, and both of those equations have nu in them. So far, I don't know which equation to use. But when we look at the question, it says that the photon has an energy of such and such an amount. Well, that's E. So we need to calculate nu. We know what E is, and we always know what h is, and so use this equation. The first thing we need to do is rearrange the equation to solve for nu. Divide both sides by h, and we come up with this equation right here. Nu equals E over h. We plug in our values. E is 2.5 times 10 to the negative 31st joules, divided by Planck's constant, which is h, 6.63 times 10 to the negative 31st joules per hertz, and we calculate, and we come up with an answer of 377 hertz. Joules cancels because joules is on the top here and joules is on the bottom here, and hertz is on the bottom of the bottom, which, as we showed before, that it's on the top of the top. Let's try the third equation. Determine the energy of a photon. So we definitely will need to use this second equation, E equals h times nu. Determine the energy of a photon of light that has a wavelength of 3.5 times 10 to the negative 7th meters. This equation would be useful right now, but we don't know what nu is. So we need to figure out nu first. So that means we have to use this equation because we're given wavelength, we're given lambda. We always know what C is. So we need to rearrange this equation to solve for nu, and then take that value of nu, V, looks like, and plug it in here, multiply by h, and we'll have our answer. The first one, rearranged to solve for nu. Nu equals 3 times 10 to the 8th meters per second divided by 3.5 times 10 to the negative 7th meters. That's given to us in the equation. 8.6 times 10 to the 14th hertz, which I didn't write down separately, but I just put it on here. And we're already starting the second equation. E equals h times nu. H is always this value here, Planck's constant, and we just got done calculating nu using this equation above, and so that's 8.6 times 10 to the 14th. We multiply these, and we end up with an energy of 5.7 times 10 to the negative 18th joules. That's how energetic this light wave is. So today, what did we do? Spent most of the time calculating the energy of light, but we also want to remember that the energy of light has to do with photosynthesis, and it has to do with energy generation, the energy of different types of electromagnetic radiation. And so we used our two equations, C equals lambda times nu and E equals h times nu, to do our calculating. That's a wrap for today, and thank you all for listening. Bye.